Welcome to another episode of Code for Thought. Writing programs to run in parallel is hard, in particular on high-performance computers or HPC clusters, because it's not just a question of getting them to run, but having them run in a performant and efficient way so it makes the most of a supercomputer. And on top of that, as you will hear later, we're not just talking about running a single application once, but a series of computing steps where each will depend on the output of the previous job, and where we have a large number of in- and output files and artifacts to manage. Being able to do all of that takes a lot of experience and a lot of skill, and many programs running on HPC clusters are therefore written in languages such as Rust, Julia, Fortran, or C++, making use of special libraries such as, for instance, the Open Message Parsing Interface or OpenMPI. Needless to say, it takes a bit of time to get into all of that, and quite a bit of time actually, but time is a luxury that many researchers do not have. Research projects are time limited, and many run on shoestring budgets that doesn't give them a lot of leeway to hire expert help. So how can you make their lives a little bit easier? Like helping them to write workflows to manage the data flow in their research apps, and doing all of that in a language that many of them already know, a language like Python, for instance. Which brings me to the subject of this week's episode, where I want to introduce you to a Python library that aims to do just that, a library called Parsl. I had the pleasure to talk to two of the key people on the project, Katz from the University of Illinois in the US, who many in the community of research software engineering may already know, and Ben Clifford, the project maintainer from Berlin in Germany. To get an overview of Parsl, its history, and what it aims to do, I had a chat with Dan first.
I'm Daniel Katz, or Dan. I'm basically a computational researcher in a lot of ways. My current role is as chief scientist at NCSA, the National Center for Supercomputing Applications at the University of Illinois, Urbana-Champaign, where I'm also a research associate professor in the School of Computing and Data Science and the School of Information Sciences.
And I believe you're also involved in a project called Parsl, aren't you?
Yeah, the story of the things I'm involved in tends to be a long story, so I start with the short version and then wait to see where things are going to go. But yes, so I'm a co-PI on Parsl. Parsl is a project that came out of an older project that was developed at the University of Chicago that was led by Mike Wild, called Swift, which is different than the Apple Swift language. And I was at University of Chicago at the time, not at the time it was started, but for quite a long period of time where I was working on that project. And in 2016, we had a proposal that we had funded to work on that. And part of what we put into that proposal is that we would look at the choices that we had made about Swift, and we would kind of try to say if we were making those choices again today being 2016, would we make the same choices or would we do things differently? And the answer was that we would do things differently, and that different way of looking at it basically is where Parsl came from.
Parsl is an acronym. What does it actually stand for?
Well, it's not exactly an acronym. You can think of it as an acronym. You could think of it as a word. So one way you can think of it is as a parallel scripting library, Parsl. You can also think of it as Parsl, as in parcel tongue from Harry Potter, as in the way of communicating. You can also think of it as parcel, as in a thing that you're sending.
You mentioned Swift. So how was the evolution from Swift to Parsl? Because Swift, I guess, was dealing with a similar problem like parallel computing?
Yeah, so both Swift and Parsl were dealing with the fact that effectively that the way that programming worked had changed to some extent, that at some point people would think about programming as they would think about instructions, and they would want to parallelize those instructions or potentially parallelize functions. And the idea of Swift and Parsl was partly that you could parallelize functions, but partly that you could parallelize external executables as well. It's effectively programming at a level of programs as opposed to programming at a level of instructions. And this was common in data analysis, where you want to potentially run some filtering on some data, and then you want to do something else to that data. And you're effectively working often with programs and files and trying to put them into a program or sometimes a workflow. And the idea of Swift was that you were doing this in a C-like language that wasn't exactly C, but was kind of like C. And in 2016, our realization was that we could actually just do this in a real existing language, Python, and not actually have to force people to learn a new language. That's basically the kind of the change that we made, was going from something that was relatively hard to start learning to something that was much easier to learn, but had very similar functionality.
Well, Python is very widely spread in the science community, but so are other languages. So you mentioned C, and there's, of course, C++ and Fortran. Fortran may be less so today, but well, it's still used in parallel computing and HPC centers, and C++ as well. So I'm sure you've been asked a few times now, why Python? Why stick with Python?
Well, it wasn't stick with Python. It was actually choose Python.
Choose Python. Yeah.
And it was choose Python over, as I said, a C-like language, but not exactly C. So we basically in Swift were asking people to learn something that was like C, but it wasn't exactly C. And so the option then at that point, which we wanted to pursue, was to use a regular language. And Python had the ability to do this, and Python particularly is often used for scripting and gluing in a way that compiled language wouldn't necessarily make sense. And so that's the reason we chose Python. We actually originally proposed to also investigate R and use R, but then our proposal was not funded at the large amount that we had asked for. It was funded at about 2/3 of that amount. And because we didn't get the full amount of money, we descoped what we were going to do, and we dropped the R piece at that point.
Okay, and Python was quicker.
We just had to make a choice, and we just chose. So I don't know if there was a great reason for that or not. In some sense, if we had chosen R, maybe we would be in a better situation. Maybe we'd be in the same situation, but we just had to make a choice, and we chose something.
Okay, could you give us an example of a use case where Parsl is useful, a scientific project or a domain where it's sort of shines and comes to power?
I'll just go back to something that I worked on quite a long time ago, where to me the need for something like Parsl in Python or even Swift in the C-like language made sense. And that was working in astronomy, where the project that I was working on was building a library that did astronomic image mosaicing. That tool was called Montage. This Montage software, because it's open source and is very, very easy to assemble into different purposes, has ended up being used as a computer science benchmark and a number of different simulations and a number of different situations, as well as being used as a production tool in astronomy. So what Montage does is it lets you take a bunch of different images that were taken with telescopes at different times. They could overlap, they could be in different projections, they could have different amounts of sky, cloud, different optical parameters that they were taken through. They can be in different bandwidths, different frequencies, basically different optical regime or electromagnetic regimes. And you can assemble those together into a single image. So that's mosaicing. You can map different bands to different colors, and you can do some blending of the edges. And the challenge is actually doing this in a scientifically valid way. And so Montage is very scientifically accurate in terms of preserving the amount of energy or the flux in each of the pixels, and then also preserving the position of each of those objects. And so what happens if you're trying to, let's say, build a mosaic, is you have a bunch of images and you may want to reproject them into a different orientation, different projection. You may want to do other processing on them. And you may need to do some filtering to decide which ones of them are actually going to fit into your mosaic that you want to build. And then you actually kind of put them all together. And then there may be some final processing if you have multiple bands that you're going to be combining. So effectively, there's a bunch of different steps that are happening. Each of those steps is happening kind of over different files or different bands. Mm-hmm. So there's lots of opportunities for parallelism, and each of those things is being done by a executable that's generated from a single C code. And so the challenge then is, how do you actually put all that together in a way that's easy to program and easy to understand and optimal or at least high performing on different kinds of resources.
And without Parsl, that would have been a lot more difficult, a lot more work, I guess.
So there are other ways that you can do this. You can assemble this all into a compiled program that uses MPI, for example, but then makes the programming harder, and it makes it harder to use different amounts of resources for different steps. You can do this with other workflow tools. Pegasus, for example, was one that was used initially when we were doing the testing and is still used by some of the people that are using Montage. So there's multiple ways of doing it, but we think that Parsl is one of the easier ways in terms of programmer effort as well as performance that you get in the end.
You're also quite well known in the software community, at least in the research software engineering community and in the scientific community, no doubt as well, for promoting software sustainability and making software not only reliable, but actually reproducible and reusable as well. So how does Parsl help with that?
I'm not sure that Parsl necessarily helps with that, but I think Parsl is an example of that. Maybe it's a slightly different way of saying it. As I said before, in 2016, we got a grant to work on what we thought was going to be Swift, but what we turned into Parsl because it ended up being a more efficient and a more useful way of doing things. So during this 5 years plus a 1-year no-cost extension, we built Parsl. We got version 1.0 released, and we started basically then kind of doing maintenance releases, which we moved to a weekly release schedule as opposed to a version schedule. When we were doing this building, we had somewhere between 2 and 4 people at different points that were working on it. One person did the initial build. Another person then came in to do a bunch of the work. When we had those 2 people working, we kind of had a lot of interesting discussions about how are we going to work as a project. It's no longer one person that just does what they want, but now we have to have agreement among 2 people. And so that set up a bunch of processes, which were quite interesting. And then as more people came in, we were able to look at those processes and sometimes keep them and sometimes change them, but at least have documented processes so that it made it easy for people to contribute, even if they weren't people that were part of that kind of core team. Mm-hmm. When the funding was ending from that original grant, we started to think about, okay, now what do? We have a tool that a bunch of people are using, some large projects, some individual scientists. Other people are building tools that work on Parsl and won't work without Parsl. An example of that is something called FuncX, which was a function as a service platform that turned into Globus Compute. And so that's now something that depends on Parsl. So we were thinking kind of how do we actually keep this going? And what we thought about was what we really need to do is to do some amount of work. There's some technical work that we need to do. There's some community work that we need to do. So we need to support a small number of staff members to do that. And we applied for funding to NSF and to CZI, the Chan Zuckerberg Initiative, for 2 kind of complementary efforts to do those 2 things, basically to make the code as easy to maintain and as easy to contribute to as we could, and to build community around the code and around the project. And we've been doing those 2 things for the last couple of years. I think you'll also be talking to Ben Clifford, who's the main developer who's been on one of those pieces. Our community manager, Sophie, has also been involved in the other one. What we basically tried to do is to think, can we bring together the resources we need in order to do this? And those resources we hope will be coming from the projects that use Parsl, from contributors, from other volunteers, and maybe from some other research activities. We are also trying to follow the model of other projects that we're familiar with. AstroPi is one of the reasonably well-known ones that's basically doing this. So kind of along this path, we recently joined NumFocus as a fiscal sponsor. That gives us a neutral place that we can work in and gives people an opportunity to join the project and to potentially become part of the governance if they choose to. So the project, from our point of view, is no longer a University of Chicago and University of Illinois project. It's now a NumFocus project where other people can come in and really be key parts of it and become co-owners of the project as well.
So in essence, you're in for the long haul.
Well, that's what our hope is. That's what our trying to do is. Whether or not we'll be successful is still a question, but we think that we're setting ourselves up as well as we can, given the size of our project, to do that. One of the questions is that this is clearly a path that works for larger projects like AstroPi. It's unclear if this is going to work for a smaller project like Parsl. That's part of our question. We hope the answer is yes, and if not, we'll be trying something else next. But at this point, we're trying to use this, and we think it looks reasonably promising right now.
Okay. You mentioned that some projects already depend on Parsl. So how many contributors are there and how many people are you aware of are using it? Or how many organizations? Let's start with that.
So how many contributors is relatively easy because it's on GitHub, and I don't actually know what the exact number is right now, but I would get it's something like 130 plus or minus. But that's a little bit of a funny number because there's kind of an 80-20 rule in some sense, and maybe even more than an 80-20 rule where there's a small number of people that have contributed a lot, and then there's a large number of people that have contributed fairly tiny bits from even maybe just fixing a typo in our README or something like that. So there's a lot of contributors. There's a smaller number that have really been the core contributors. But I think all the contributors are valuable. And part of what we're trying to do, again, is our sustainability model is that once somebody does contribute in whatever way, whether that's into the code or by using it or by doing something else, then we want to try to get them as involved as we can. So again, some people may come in and they might do something small at the beginning, and then maybe they'll see something slightly bigger that they can do later, and then maybe they will become a core contributor. In terms of usage, it's really almost impossible to know anything about usage. All right, Parsl is open source, so people can download it. They can get it from PyPy. They can get it from a bunch of different places. It can be installed on some supercomputers, which is the case in some of the US DOE and NSF-sponsored systems, in which case we don't even know that people are getting it because they're using it based on somebody else's installation. I'll tell just a brief story about usage tracking, which we tried to do. So when we started, we knew that knowing our users would be important for future funding requests. And we designed opt-out usage tracking at the beginning and made this very clear in our documentation and everything that this is what was happening. And if you didn't want your usage to be tracked, it was very simple for you to turn it off. And most people were fine with that, but a couple of people were very vocally not fine with it. And so we changed our model to opt-in usage tracking. And basically, we lost almost all of our usage tracking at that point because it was very hard to convince anybody that they should do this extra step. We've recently moved to multiple levels of opt-in usage tracking, from extremely minimal to something that is still, we feel, quite anonymous, but gives us a little more information about what's going on. And we are putting that into our examples and our documentation to make it clear that we would appreciate if people can actually do that. Again, it's completely up to them whether they do or not. I guess the quick answer is that at one point we had a good picture of usage, then we had basically no information about usage for a long time, and now we're starting to get a little more information about usage. The thing that we get that's even better than usage, though, is citations. And so when people cite Parsl in papers, that's actually much more helpful for us because it doesn't necessarily tell us a whole lot to know that somebody is using Parsl and they're running a 16 CPU job on a system for 30 minutes. It's much more useful if we can see that this paper that created the scientific result used Parsl, or the system that is being built for an astronomical telescope is using Parsl as part of its core processing. So that's the thing that's actually more useful for us, is not just usage, but what is that usage? Who's doing it? What are they getting out of it?
Well, I think there's a whole different debate, monitoring usage, etc., and user data. And I can understand that some people feel uncomfortable with it today. As a final question, you already alluded to that things are looking good, but what keeps you up at night about Parsl?
I think things are looking good in a lot of ways, but they're not looking 100% good. The model that we have now, with a relatively small amount of a core developer and a relatively small amount of a community manager, right now it's 1 FT of a core developer and half an FT of a community manager. If we could sustain those two things, I think we would be fine for quite a long time. The challenge is, can we sustain that kind of FT and a half? And if not, what can we actually sustain? And that's not clear right now. And the challenge isn't that we don't know what we need, it's that we don't know where we can get it from. So we're getting a little bit of support from one large project. We potentially can get a little bit of support from another large project. Effectively, it's very easy for us to, well, I shouldn't say very easy. It's relatively easy for us to get people to contribute to Parsl. People contribute based on kind of their use case and satisfying kind of what they're interested in. That kind of core work to make sure that Parsl continues to work for everybody isn't something that really is any one person's need. And so that's kind of where we have this issue that we kind of need this ongoing resource, this ongoing people, this ongoing staff to actually coordinate all those individual contributions that we are getting. And some projects, I think, understand that and they're willing to help us support that, but it's not clear yet if that's enough to actually maintain the minimum part we need. And that's what we're really working on at this point. I should mention, just as we wrap up, that Ben has been the main developer for the last couple of years. There's a number of other people that have been quite involved. Kyle Chard is the PI of the overall project at this point. Yadav Babaji was the person who did the initial development, and Sophie Boy is our community manager. And so all of them, as well as all the other contributors, have been key to where we've gotten to now. And it'll be interesting to see how your conversation with Ben goes, because I think that's really key about where we go in the future.
As I mentioned in the beginning, Ben is the maintainer of the project and therefore a key person, as Dan has just said. With Ben, I wanted to dive a little bit deeper into the technical aspects of Parsl, but we also returned to the question of usage and what it means to be a maintainer for an open source project like Parsl. Some of the listeners may remember Ben from an episode I did on GitHub project management a little bit earlier in the year 2025. So over to Ben now.
Hi, Ben. Nice to see you again. And Happy New Year. At the time of recording, it's just freezing January, at least here in London it is. I don't know what it's like in Berlin.
It's freezing.
Yeah, that's what I remember Berlin to be, at least in winter. Anyway, we're going to talk about Parsl because I think you are the key developer, aren't you, or the core developer of Parsl.
I'm the maintainer at the moment.
Yeah, I think that there's the kind of lingo that we need to get right, isn't it? So there is core developers, then there's the maintainer, etc. But from a developer's point of view, so we heard from Dan earlier, what are the key concepts and advantages of writing code with Parsl? Why would we want to do that?
Okay, so there's two things going on. One is if you're used to writing for your laptop or your workstation, for example, and now you want to be scaling up to a supercomputer or a cluster or even just a handful of machines, you encounter a huge pile of technical issues that aren't part of your core science problem that you don't have on your laptop.
Okay, like what, for instance?
Well, there's a network connection between the two computers. So on your computer, you've got a motherboard and a hard drive. And if the connection between those two fails, you just accept that your computer is broken, right? This is not a normal thing to be happening. It's my laptop is broken. I'm going to give it to a technician. This basically doesn't happen. When you're getting up to big scale machines, that sort of problem, not between hard drives particularly, but other connections between the pieces break all the time, randomly. So you can't just give up on everything every time that happens. That's an example of one of the kind of problems you then suddenly have to start coding around. Like I went off to do a bit of a calculation and it mysteriously failed. But now I run it again straight away and it works this time. That's not how your laptop works.
No, not really.
So there's a sort of huge pile of things like this that they're not core to your science. They're just an attribute of running in that kind of distributed environment. So you have all these problems. And one of the things with libraries is it's nice to go to the internet and download a library that solves your problem. And that's that's one of the big goals of Parsl, that we're solving those dirty engineering problems so that you can think about your science. And that ties into the other big advantage because we're a Python library. So many people can do stuff in Python.
Right, indeed.
Never encountered a language that is so widely supported in terms of my random friends who don't work in computers, but they can program a little bit of Python. And therefore they would be able to do a little bit of Parsl.
One of the concepts of Parsl is the workflow, isn't it?
Yeah.
What does that actually mean, the workflow, in concrete terms? And how is that set up and used?
Our model for how you interact with these big distributed systems where you get failures and you can use lots of different computers at the same time and all of that is that you try and divide your application into a small set of tasks, which you can write in Python or some other languages. And then you stick those tasks together and Parsl knows how it can run those tasks and how it can retry them and how it can make them work in this complicated environment. And at that technical level, a workflow is how you stick all those tasks together, which you express in Python as well.
Give us a flavor of one of these task lists, for lack of better word.
Okay, so one of the science applications I work on is astronomy. And what that looks like is you have many hundreds or thousands of images from a telescope, which is an automatic telescope. It takes pictures every 30 seconds, basically forever. So you have a huge data set, and with each picture, you know where it was pointing and when that photo was taken. So one of the tasks is to say we want to overlay all of these pictures together to make one giant atlas of the sky. There are various things that can happen concurrently, can happen in parallel. Every photo is only a piece of the sky. So you need to shift it round into the right place on your big image. And you can do that separately for every single image. If I have 1 million photos and I have 1 million compute cores, I can use all of them at once. Or I can run 1 million photos in sequence on one core. And so each of those would be a task. And then when you have images that overlap, you need to merge them together And so another task is these images occupy the same bit of space, the same bit of the sky, and I'm going to merge those together. And that can also happen separately from processing merging other pieces of the sky. So that would also be a task. And then the workflow is the piece of the code that knows which images need to be stitched together and which images need to be placed wherever.
Okay, you gave us a flavor of how the tasks are being organized or can be organized in this workflow. But how does it all put it together under the hood? What's the architecture look like of Parsl? Is that something that you can actually explain in words easily without a diagram, which unfortunately we do not have in a podcast?
Oh, without a diagram. You can maybe imagine as one part of the workflow code just tries to make a stream of these little task descriptions. And you as a science user make a workflow description, and then what's going to come out of that layer is just a sequence of tasks that need to be run. Mm-hmm. And then the other half of Parsl, you can sort of imagine a dividing line. There's the sort of description side of things. How do you describe what your tasks are? And that's what we try and make look like Python for users. And so we've got a bunch of libraries that try to twist the Python language into a way that generates tasks rather than just executes your code. Then we've got this stream of tasks in the middle that the user theoretically doesn't care how they get run. Like, we want to get them run, but we don't care too much. And then the other half of Parsl runs those tasks. And we actually have collaborations with various different groups on how those tasks get run, because it's a fairly neat modular description. So various people have made engines, executors for executing these tasks on Parsl. So with one description, you can switch between different research groups' execution systems because we have this standard format. But what that looks like for our main engine, our main executor, is we run a little program on every node of a cluster, and that little program just says, all right, give me a task. I'm just going to run a task. That's all I know. Is my job is just to ask for a task and run it and give the result back and ask for another task. So you have all these sort of little workers all around your cluster that they really know nothing about your structure. Their job is just to ask for a task from this stream.
Okay, so we've got this rather neat separation. So the back end, if I may call it like that, that interacts with the actual machinery.
Yeah.
That needs to be probably adapted to different hardware platforms because, after all, I think you can actually run it on your laptop as well as, a supercomputer somewhere.
Yeah.
So is that something that you work then with? You alluded to that already, but is that something that you work with groups then to adapt that to particular machines? They have similar operating systems anyway, I think Linux.
Yeah, everything's Linux these days.
Indeed. So there's still hardware differences.
Yeah. There's two kinds of groups we work with on that side. One is software producers. So what they are producing is software that can run this kind of task.
Right.
For them, Parsl is interesting because it's a good source of tasks to run. So they want to make software that can run tasks like this, and they're happy for anyone to stick their stuff on the front to feed stuff in. That might often be going towards someone's PhD or a software research group's product or something like that. And then the other class of people we work with are the people who run compute sites.
Right.
So they run an HPC center. They don't particularly care about the software for the sake of software at all. What they want to do is help their application users run their science on their supercomputer. They sometimes make code contributions to Parsl, but they're much more interested in really tweaking the config file very seriously to work with their site, which I don't mean to diminish that in any way. Like, tweaking the config file sounds not very much effort compared to writing new software.
But it is.
But that's actually getting that working, getting that performant is a serious piece of work. And getting it performant is the important thing, right? It's not just about getting it running. The point of running on a big HPC system is to use it effectively and use it in a performant manner.
So that requires a lot of interaction between Parsl and the various different, what shall we call them, stakeholders?
Yeah,
right.
Stakeholders is a good word there.
I know there's you, the maintainer,
yep.
and there are other people like Dan, and there's Kylie, I believe, in the US. But how is this collaboration working? Where is it all glued together?
So from my personal perspective, I like to just live in GitHub and Slack and do stuff there and not be putting too much effort into establishing formal projects with weekly meetings and things like that. Some of my other colleagues who are more in that structure, they have weekly meetings with people. It just fits the working style of whoever happens to be involved.
What do you say? So it's the code maintenance, the code hygiene, and the addition to the Parsl library and pull requests, etc., which you can perfectly manage through GitHub.
Yeah.
But there is also what I would call the kind of acquisition side of things, where you get new groups on board. And how do you do that? So there's a little bit of perhaps hand-holding is too strong a phrase.
Yeah.
That kind of effort, which is distinctly non-coding. And that's something that is done by the others then.
I do it a bit. One of the nice things with Parsl is it's got to the point where we are not having to do a huge amount of outreach like that anymore. Users find Parsl. Users encourage other users to use Parsl.
Okay, so it's got this kind of momentum now.
It has enough momentum where users appear, which is, for an academic project, that was quite surprising when it started happening, because when you begin an academic project, you spend a lot of time trying to convince people that your software is worth using, right? And sort of keeping track of every single user and how they appeared, right?
And send them love letters.
Yeah, right. And Parsl's at the point where we are beyond that. Just. Okay.
It's not exactly the number of users, because, it's not like everybody with a PC or everybody with a laptop would go there.
Yeah, I mean,
you get people like that, but I mean, there are sort of the clusters of supercomputing centers, which is more limited.
Like a couple of supercomputing centers on their internal site documentation say, here's how you use our supercomputer. And they have a handful of different software systems, and how to use Parsl on that system is documented there. Right. And you can write to their support as a first line question. And so I removed all the documentation for those sites from our documentation and replaced it with a hyperlink to their documentation.
So what's the user base like then at the moment? And how many of them are actually contributing? Because I read a book recently by Nadia Iqbal about open source software. The users of software, open source software, breaks down into very few people who contribute a hell of a lot, and then a large group of contributors who contribute very little, and then an even larger group of users who contribute nothing at all and just consume. What's it like with Parsl?
Yeah, it looks like that. I'm the only person paid to really be heavily working on Parsl for the sake of Parsl. So if you look at the graph of pull requests, my contributions are completely crazy. And then there's probably around 5 to 10 regular contributors that are a broad mix of application users, some of the people who build the execution backends, a couple of site people put in occasional changes when they need to, because they need that. It's very common to have very occasional drive-by student pull requests that are sort of one-off. I find that a bit frustrating because I don't want to be discouraging to people making requests, but your first pull request is going to be extremely expensive, right? And full of like a lot of effort, a lot of time on everyone's part. That bit is a bit frustrating because if you just do that once, we've put the effort in to get you on board and now you don't come back. That's sort of the nature of working in academia, where you have a lot of people who pop up for a summer project or a one semester project and then they leave.
Yeah, well, it also seems to be the nature of open source projects where you have actually contributors who may submit one pull request and then never heard of again, or maybe half a year later. It feels like a lot of effort. Yeah. Do you have to say no often then, sort of that pull request? Not so much, do this, that, and the other?
So almost never say no to any pull request ever, but it's relatively frequent that people get tired of my review comments and walk away.
But you do it politely, don't you?
Yeah. I mean, we have a lot of automated testing, and sometimes they walk away because they can't satisfy the things we specified in our automated testing as well. There are barriers there. That, again, I found for a lot of academic software is very used to just doing a project and then dumping it in whatever state it is into the main code base. And having much more stringent quality controls on code is culturally quite surprising for a lot of academia.
Yeah, well, yes. Hence this podcast show.
Yeah. But I think it leads to things where people do their project. They kind of feel like, well, in the last couple of days, I'll quickly tidy it up and get it merged. And it's like, no, mate, you've got to spend as long again. If you've just been hacking on it and doing nothing wrong with making hacky code. I do that the whole time. It's great. And you don't have to deal with making the code nice.
But when it goes into production...
you can't just then say, well, actually, this billion-dollar science project is suddenly stalled because my random summer hacking is now affecting you.
So we're coming to the end now. I'd like to ask two questions that people who are new to Parsl may ask themselves. If I'm new to Parsl, where should I start?
You can go to parslproject.org. We've got an interactive tutorial that you can play with in a notebook online. If you want to be a bit more passive, you will also find a link to our annual conference, Parsl Fest. And the last 4 or 5 years, we've had videos, I think pretty much all the videos for all the short talks, the little 7-minute talks on a range of topics. You can go and have a look at what people are doing with Parsl there.
Where was the last Parsl Fest?
So Parsl Fest is usually it's always been in Chicago.
Oh, right. Okay.
The sort of origins of Parsl come from the University of Chicago. So it's sort of 50-ish people.
Well, not that small.
People, about 50% of people give a talk. We stick really hard to a 7-minute rule. So the pace is extremely high. Nobody drifts off into very boring depth. You've got 7 minutes to present your science and how you use Parsl to do it.
And that's it.
Yeah.
Okay. Finally, and I think you touched on that already a little bit with GitHub, but if somebody is brave enough of saying, I would like to contribute to Parsl, just run us through what they need to do in order to get it done and get it into the code line.
Okay. So you've got to find something that needs doing, and that might be something you have discovered, or it might be something that there's an issue for. If it's something you've discovered, I encourage you to talk about it. You can talk about it on Slack, or you can make a GitHub issue and figure out what the code changes are going to be. Then you can make a pull request, and the CI will fail because no one's CI ever passes the first time. And you'll get code reviews there are 2 or 3 people who tend to do code reviews, and you'll probably get feedback on that and then fix that stuff. And then we push merge.
Okay.
And then we have automated releases every week. So maximum 7 days after we push merge, your commit will be in a release.
So we're at the time of recording at the beginning of 2025. So what's in store for Parsl in this year?
I have funding to do a lot of reliability work. And so there's some stuff there that doesn't look like features. It's just going to be a bit more reliable, I hope. We have a big other project called Globus Compute. They share a lot of our code base. It's a bit of a strange relationship, but there's going to be a pile of minor interesting features. I hope task prioritization, some better ways to describe your tasks coming along. One big feature I'm working on is really how to do performance analysis. If you listen to everything I've said about Parsl so far, it's about describing your workload. Then I said it's important that it runs performantly. And we're a little bit weak on, you can see it runs slowly, but you can't really see why it's running slowly. Right. And I've done a lot of prototyping work there, hoping to make that into something a bit more producty.
Okay.
Understanding why stuff doesn't behave like you think it should.
Well, I hope that piqued your interest in Parsl, and maybe you want to check it out next. As per usual, you'll find a few links in the show notes. The links to the Parsl project, of course, and the GitHub account for sure, but also pointers to some of the other projects mentioned during this episode. And if you feel brave enough to dive into the world of parallel computing a little bit deeper and with another programming language, in early 2025, I worked with my ex-colleagues at the University College in London, in the UK, on creating a podcast for a course on C++. It's a companion podcast for a 10-week course at UCL, and parallel computing is covered in the last part of the course. So if you'd like to find out more, why not head over to the podcast called For Code in Research, and you'll find the link in the show notes as well. In 2 weeks' time, I'll return to a conference that has a firm place in the free and open source community. I am talking of FOSDEM, of course. The conference takes place every year over the first weekend in February in Brussels in Belgium. And this year, I made my way to FOSDEM to cover one of the many workshops, or developer rooms as they're called, the one on open science. There were a lot of interesting talks, and you'll hear from very different people and research projects that use open source software in their work, so I do hope you'll tune in then.
Oh, time's up. See you next time. But before I forget, this podcast is covered by the Creative Commons license. See ya!